So the question that arises is, why are we talking about Newton's law of universal gravitation in the uniform circular motion unit? And it's because we're going to talk about orbits. And for the sake of our class, you can picture like an orbit's basically like a circle. Maybe it's got a slight eccentric kind of thing to it. It's not a perfect circle. But unless they say otherwise, you can treat circular motion or uniform circular motion in orbits kind of like, you could treat uniform circular motion as the tool that you can handle orbits with. There will be questions probably on the test where they say it's an ellipse. If that's the case, we have to use a different tool, probably angular momentum. So just be careful. If they say uniform circular motion and they're talking about planets, you can totally do the tools and the things we're about to talk about. If they do say the word ellipse, then you're going to want to use something different, probably angular momentum. All right, so let's rock on. Let's draw the sun. And I drew my own planet because I was kind of had an ego. I said planet Laurentis. And planet Laurentis is orbiting around the sun. And I'm going to have you watch a really cool video, but it describes gravity more because when Newton pictured gravity, he said with anything with mass has a gravitational pull. And the more mass, the more Fg, right? And if you're farther away, if r gets big, it's inverse square, so the gravitational pull gets less. But he had some problems with this conception because he didn't know how fast gravity traveled, right? Like if you picture the sun burn out, does this planet instantaneously just fly off tangent? Or does it take a certain time? And if that's the case, how fast does it travel? It wasn't to the time of Einstein that Einstein said, actually, it's a little more complicated. The sun, because it has mass, bends the fabric of space-time, similar to how like if you sit on like a mattress or a couch, you kind of bend that surface. So somebody kind of, if somebody's sitting next to you, they kind of like go toward you. Einstein said, hey, this sun, if it's really massive, it bends space-time more. So that's how gravity communicates in gravitational waves. And so like let's picture the sun burned out. This gravitational wave would travel from the sun to planet Laurentis here, and it actually travels at the speed of light. So Einstein postulated that, and like 100 years later, there's a team that found gravitational waves. So Einstein postulated that gravity travels in these waves, and 100 years later, people confirmed what he thought existed the whole time. So that's how smart he was, that 100 years later, we're still figuring out what Einstein was talking about because he was just way ahead of his time. So that's not going to be in your AP test, just kind of cool. This sun bends the fabric of space-time because it has mass. Planet Laurentis has less mass. He's also bending the fabric of space-time. And what's happening is he's going to travel counterclockwise around this circular orbit. I'll call it uniform circular orbit kind of deal. And that's my VT. And I would want to fly off tangent, right? That'd be bad for my planet. Every time planet Laurentis wants to fly off tangent, the force of gravity felt between planet Laurentis and the sun pulls inward. So it's a centripetal force, right? Because every time it wants to fly off, it pulls inward. Let's say I'm later on in my orbit. I found a pink pen. I want to fly off tangent, right? So I'm going to fly off tangent, but then the sun says, nope, Fg is pulling inward. And a really important thing to highlight, remember, for every action, there's an equal and opposite reaction. So people always get confused, like, well, that's a big object, that's a little object. Surely Newton's third law can't apply. It does. I'm pulling on the sun with the same Fg. The only thing is, the sun doesn't really notice, right? Because if you had F equals ma for a certain force, if the mass is so big, the mass of the sun is so large, that it's not going to like really notice me. It's not going to accelerate or do anything crazy. It'll accelerate a little bit, obviously, because F equals ma. But if the F is what it is, and this mass is so big, it's not really going to notice that I'm pulling on the sun. Kind of like if you go skydiving, the Earth's pulling you down, and you're pulling the Earth up. It's just that they're equal opposite forces. It's just that the Earth's mass is so much bigger. So this is how it ties in, to answer the question, this is how it ties into uniform circular motion. Uniform circular motion, we use it when there's any force pointing toward or away from the center of a circle. So obviously you can see as I orbit around here with planet Laurentis, there's a force of gravity pointing inward. And you might be like, okay, the force of gravity, how do we do this? Step 1, we draw a picture. Step 2, we label our forces. Step 3, you pick your coordinate system. It's almost like the steps I've been teaching you all year are still gonna work. And don't forget, sorry, that was sarcasm. Of course they'll work. VT is not a force. So if they ever say draw an FBD, don't put the tangential velocity on there because it's not a force. You could make a note of that. You could say it's too close to my liking. It almost looks like it's touching my dot right there. Just keep it farther away. The only force acting on this planet is force gravity acting inward. All right, so step 1, picture. Step 2, we labeled our forces. Step 3, we picked our coordinate system. And the coordinate system over here, it's lined up. You could do that. It's still lined up along the axis right there. And so now we're actually going to go through and do our business here. Step 4, we're going to sum our forces. It's the same thing we've always done. So don't pay attention to this yet. The force of gravity is the only centripetal force, and we set it equal to MAC. An important question, when we're summing our forces on planet Laurentis, Fg, what M is that? Well, since we're talking about planet Laurentis, that's going to be the mass of planet Laurentis right there, because that's the planet we're talking about. We're doing it from this perspective. Now here's the big thing. Fug equals mug, except when you're talking about planetary stuff and you're not near the Earth's surface. So fug equals, oh, I made a note here. I said, you can't say mug. You can't say it because we were talking about big objects that are nowhere near the Earth's surface. Smiley face, exclamation point. So this is a fine thing to write, and you'll get a point for that. Don't skip that step because that's a true physics statement. I just redrew FG over here. I said mass Laurentis times AC. Remember, a net force inward, like force gravity, produces a net acceleration inward as well. So net forces produce net accelerations. And they say Laurentis is going at constant VT. I keep changing direction, so I am going to have an acceleration. So now we're going to plug things in. Force gravity is, just to be clear, it's from the center of the sun to the center of Laurentis. And so you would actually technically have to know, and just be careful how they write this, what's the radius of the sun? How far away is it right here? And what's the radius of Laurentis? Or they might legit say from the center to center, but just make sure whatever that R is, it's from the center of there to the center of there. I've even heard them say something like, the radius of the sun is this, or a planet, or whatever you're talking about, and this altitude above is this, so you just want to make sure it's from the center to the center, whatever goes in for your R. They won't be that tricky. Just be careful in case they phrase it funny. So we do this right here, and you're like, wow, big GMS ML over R squared, mass Laurentis AC, and something sweet happens. What do you notice about the mass of Laurentis on both sides? Cancels. And so that leads to a huge idea. Things orbit not based on their mass, but based on the mass of the thing they're orbiting around. And that's a huge idea. They might say, all right, you're orbiting, and then you double the mass of your planet as you orbit, has no effect. Because remember, the sun is bending space-time, and you're orbiting around that space-time right there. And you're like, wow, that sounds kind of like cool, more difficult physics. Yeah, you're doing some cool, more difficult physics, so it's neat. So what I'm gonna have us solve for is that we're gonna solve for the orbital velocity VT. That's kind of a nice thing because we're gonna figure out how fast VT this planet Laurentis is orbiting. Now picture this. If I were orbiting more closely to the sun, FG would get pretty big, right? Like you'd want to pull me inward. And like I said, if we're going slow, it'd kind of like, oh, Laurentis, into the sun. So we don't want to be going so slow that gravity wins and we go into the sun. And we don't want to be going so fast that we fly off tangent. But our gut does say, our physics gut, if you're closer, you're going to feel FG more strongly because the R shrunk. So you're probably going to have to be going faster to maintain a stable orbit right there. And if you're far away, your gravitational force pulling you inward is less. So you can't be going too fast or else you're going to fly off tangent. And remember, that's bad for our planet. Okay, if you want to name your own planet, you can call it mass of whatever you are. That's kind of fun too. So we have this right here with itself for orbital velocity. Oh, look, we have an R squared, we have an R. One of those cancels over here, and that one goes away right there. And you get that right there. You take the square root, and that's what they call the orbital velocity equation. And this is for something orbiting the sun. You can orbit lots of different things in uniform circular motion, but we just did Laurentis around the sun. So let's check it out. If the mass of the sun is great, so this side of the equation gets big, that means the gravitational pull is going to be big, then you're going to have to go faster to have a stable orbit. If you're really close, so this bottom part's getting small, as that one gets small, your VT will have to get bigger because remember, we said as we get closer, whoosh, like that, you have to be going faster because that gravitational force is getting stronger, so you don't want to be succumbed by the sun, right? So that's your stable orbit right there. And you know, satellites that orbit the Earth, they do come down because they burn up in the atmosphere. They're in a stable orbit as long as they're maintaining that velocity. All right, so we have that. And so what did I say? Yeah, you have to maintain that velocity so you do not spiral inward. So we have that, and we're just gonna finish with one last little thought here about orbital velocity. Oh, I made a little note. I said, here's our orbital velocity equation, and this one does show up on the AP test, and you can derive it. We just derived the equation. We summed our forces, and it's kind of fun because you're literally just making your own equations now, and that's how awesome physics is. You don't have to rely on an equation sheet. You just made your orbital velocity equation. But it says, or the mass or whatever you're orbiting. So I said, in the case of the sun, we are orbiting the sun, but you could be doing a moon around the Earth. There's a really cool news story about how an old rocket engine was orbiting the Earth. Anything with mass, you can orbit. So you have that. And I said, what happens if the mass of the sun were times 4? Like we went to a different solar system and the mass of the sun was times 4. Times 4 here gets a factor of 2. So if you ever had a more massive planet by a factor of 4, your orbital velocity would double. And that makes sense because you have more gravitational pull, so you have to be going faster. And Einstein would say MS is bending space-time more. So if you picture that, like you're sitting on the couch and you're bending the couch cushions, and if you like had like a weight on you, you're holding that as well. You bend it even more. So you don't want the person next to you get gobbled up into your space-time bending there, so they'd have to be going faster as they orbit you. My analogy kind of broke down there, but all right, we have one last thing to do.